How's it going? Audio, I think it's working perfectly. Excellent. So what I wanted to talk about today is you now have a choice of how you choose to store data. And we're familiar with relational databases. They're the technology incumbent. Being around for so long, sometimes it's hard to remember some of those founding principles that they had and some of those behavior characteristics that they intend to have in how you access your data and make sure that it's safe. So the talk that I'm giving, I will use MySQL for examples. Obviously, I work on the MySQL product, but it should be applicable for 90% of all databases. I won't necessarily point out where those exceptions are, but if you see one and you want to ask a question, I love it if you ask questions during the talk. I think it'll make it nice and interactive. So we're talking about really under concurrency, under multi-users accessing a system, what unsafe situations can happen and how to databases sort of prevent that. Quick intro slide, not so relevant today, but if I do mention any dates of any upcoming features that we've announced for MySQL, it should be informational only. And just 2 minutes on Oracle. We're celebrating our fourth birthday just last month, of being the steward for MySQL. Very proud. These are the things that we've done in the last 4 years. We've released 2 major versions of MySQL, MySQL 5.5 and MySQL 5.6. Tomorrow, same time, I'll be giving a talk on MySQL 5.6, describing how it's really good to be able to use in an operational environment. There's a lot more diagnostic information. And it has things like online DDL, so you can add indexes without blocking users from writing to your database. Also, under Oracle, the MySQL team has doubled in size from what it was at the Sun acquisition. We now have hundreds of people working on MySQL, and the QA team alone has tripled. But for today, what we're going to be talking about is, as I said, those database characteristics, broken down into an agenda of really just 4 points. And at the end of it, I'll try and recap and say what your responsibilities should be as an application developer. The live demo, point number 2, is the one that I'm a little bit scared about, tempting the demo gods. But I think it's the best way to demonstrate it. We'll have a multi-user system, and we'll try and see some of these errors or these situations arise. So let's start off with table locks, row locks, and MVCC. So let's say that we had a relational database system that's called an accounting system. This is the easiest way to draw a demonstration. And in my customer accounting system here, I have 3 tables. A table for customers. Customers have invoices, and the invoices have items. And I've tried to color code this a little bit so that you can see the relationship where invoice number 1 belongs to customer number 1 and has invoice item number 1 of invoice ID 1. And what I want to do on this customer accounting system is I want to do an operation. And the simplest operation that I can do is I can do a backup. So I'm going to start my backup, and I'm going to read through the customer table. And then I finish reading the customer table. And I'm going to read through and start backing up the invoice table. And I'm still reading the invoice table. Let's say it's a very large table. It's a concurrent user system. While I'm reading the invoice table, somebody else does a modification, and they insert a new customer, customer number 4, and they create an invoice for customer number 4 that has some invoice items associated with it. So I'd already backed up the customer table. I'm in the process of backing up the invoice table, so let's finish backing up that invoice table. And then when I finish the invoice table, I back up the invoice items table. And then, as far as I'm concerned, my backup is complete. Or is it? Everyone see the problem here? What happened was that I read through the customer table. I finished with it. I didn't see customer number 4, and then I started backing up through the invoice table. So if I were to do a restore of this system, what was really backed up was not everything. We were missing this essential row here. So of course, if you use something like MySQL or you use another relational database, they don't allow this situation to happen. This is an example of a naive situation that they have to prevent from happening. And why this is problematic is that if we were to restore from backup, obviously what could happen is the next user that gets inserted into the customers table, they end up having these corresponding entries already sitting there in those other tables. So that there's like this security/data privacy concern. So I showed this with a backup. Backup is an easy way to show this potential race condition that exists. And the way that the database solves this problem is they say whenever you do an operation, and actually the type of operation doesn't matter. Mine was a backup, but it could be just a simple select. That operation, it has to represent one single point in time. It actually doesn't matter when. It could be the start, or it could be the end. So you could have a backup that nobody can make any changes while I'm doing the backup, and then that might kind of represent the start. Or you could have some roll forward segment to be able to catch all those changes that happened while you're backing up. It actually doesn't matter. What matters is that it's a single point in time. And the other thing that doesn't matter, as I said, is not necessarily just a backup. Anything is supposed to represent a single point in time. So that's the naive case. Let's look at how something like the MyISM storage engine for MySQL would prevent against this race condition happening. So we want to do a backup. What do? Bam, we lock all tables. We say other people, they can read data, they can read this information if they want, but they can't write to it. If they write to it, we could get in that situation that we just did not want to happen. We know what we want to touch. We want to touch all of these tables, so we need to agree to lock all of those tables in advance. And if you use something like mysqldump, it will do this. And then when you've acquired all those locks, then you can safely read through, and you can get all that data, and you get a single point in time. The point in time represents both the start and the end of the backup because nobody's doing anything. You're the only one that has access to that system. How does this feel like for concurrency? Well, readers can coexist, but writers can't. They're just forbidden. If you use something like mysqldump, it will responsibly lock all the tables in advance. If you do a single query on a single table, it will lock the table without you having to explicitly ask for it. It has this table level locking internally. So this is one way of solving this problem. Let's look at another way of solving this problem, and let's look at the InnoDB storage engine for MySQL. And actually, most other databases behave a little bit closer to this. What we have here is the same data, but in the row header, there's some hidden metadata, a couple of extra columns, where we have a transaction ID and we have a rollback pointer. Hidden metadata, and I'll show you how these work in a second. But the transaction ID is the important point here. What it is, it's similar to when you go to the DMV or the deli, you get allocated a ticket, and that's the ticket that you're going to be served with. It's a monotonic number, which means that it just only advances. Everybody gets allocated a ticket. So here we can see that our initial data was ticket number 123, and our modification that happened partway through our operation was ticket number 401. This hidden metadata. So that's actually, I'll skip this slide. Let's show what happens when we do the backup. We read through, and we cover our eyes, and we say, I'm not going to see a number greater than 394, because my backup, it was running as ticket number 394. So if anyone inserted new data, and they inserted as, say, ticket number 401, I'm just going to skip it. I'm going to completely ignore it. And actually, if I have to see a previous version of the data, this is a technical implementation, where the number is higher than what I expect, I can follow a link to some internal space called undo to be able to find earlier versions of rows. And there might be many additions of the same data in this database management system, many generations of a row. So this algorithm, where we keep this extra metadata and we keep multiple versions of a row so that we can read through here, means that we don't block writers, because readers can get that single point in time, that consistent view, just by paying attention to these coordinates or these ticket numbers. And it's called multiversion concurrency control. It's really nice because reads can happen and writes can happen at the same time. Readers don't actually set any locks. They just see older versions of the same data. And if actually someone's held a lock while they write and modify something, we don't have to pay attention to that lock either, because we can just look at a previous version of the data. It's this contextually dependent view of how we see the data. So I'm going to do my live demo with that introduction and show how this works with some sample data. And the sample data that I'm going to use, it's a geography database. I have all the larger cities of the world, about 4,000 rows imported into MySQL. I have two sessions, session 1 and session 2, and we're going to simulate where these two users are modifying data at once. So let's start a transaction in both sessions. Let's start a transaction in session number 2. Let's select the city from the city table, where name equals London. And we see that there are 2 rows. I live in Toronto, Canada, very close to the fake London that exists here. Oops. Okay. So just so I'm not cheating, we can see that we see the same data in both sessions. And we've got a transaction open, so let's modify fake London. And we'll say update city, set name equals fake London, where ID equals 1820. Okay, so if I were to read this data back, I've updated fake London. Now I only see London. What does this other user in session 2 see when they try and read back London? They see both of the rows. This is the intended behavior here. I'm allowed to see my modification, and I haven't committed it, or I haven't rolled back. I still have that choice. While these changes are pending, and actually dependent on something called isolation as well, this user is not supposed to see those changes. So let's modify another row. Let's update Paris, just to show that this is bidirectional. So I've updated Paris, so if I try and select back, I should see that there's no rows for Paris. And this particular, in the other session, I should see that there's still a row. Multiversion concurrency control is the algorithm working here. Let's modify one more. Let's modify San Francisco. Oh, and I spelled it wrong. So it found one row, it modified that one row, and now San Francisco is called not Paris. So I've made 2 changes here, I've made 1 change here. Let's try and modify in this session Paris. Bzzz. Doesn't quite work. So as we're making these modifications, we're actually holding row locks internally, wanting to modify that data. So session 1, we modified London. Session 2, we modified Paris and San Francisco. Session 1, we tried to modify Paris. And so here what we're doing is we have a lockweight. we're waiting for, by default, 50 seconds for this session to either commit or roll back so that we can acquire that lock. This session is just going to sit and block waiting for that, or waiting for 50 seconds when the timeout happens. If this were to commit or roll back, this statement is going to apply immediately. I will wait for it to time out. There we go, just so we can see what the error looks like. This session, I should say, the transaction's still open. It's still modified that one row. This attempt to modify this row was unsuccessful. I now have a choice. I can either try and do something else, or I can try again and see if that modification will be successful the second time. Let's try again. So we're waiting 50 seconds. We're waiting 50 seconds, and while we're waiting, let's see if I'm fast enough, and let's try and modify London. Something different happened that time. This one had locks on London. This one had locks on Paris and San Francisco. This one tried to acquire a lock that this one had. This one tried to acquire a lock that that one had. It's like a dog chasing its tail. It's just never going to end. So internally, what happens here is we have deadlock detection. And we realize that, these two things are just butting up against each other. And forcibly, the deadlock detection steps in, and it chooses to kill one particular transaction. It tells me here, it tried to kill this transaction. So everything that was open, in this case I'd modified London, it's gone. Those changes don't apply. And the application is expected to be able to catch that particular error. This transaction doesn't even know that happened. It's able to do whatever it wants. It can freely commit or roll back or keep making more modifications. Any questions with that example?
How can you tell which session wins, basically?
Oh, which session waits?
Well, no, which session wins? Which change is applied and which isn't?
I think it's coming up in a couple of slides, but I'll answer the quick version. It can technically kill either one. It chooses to kill the one that's made the least changes so that it can not have to roll back so much work. So it's a weighted-based algorithm. It's not time-based.
Right.
Yeah. Another question? Just...
Well, please do tell if it's too little time to explain, but or is it coming later? But could you explain how different transaction isolation levels affect locking and deadlocks?
I will, I think.
Okay.
Yeah, I don't know if I'll explain the locking, but I will explain isolation levels, and then I can try and re-answer that question. But it is true that isolation changes locking.
Hi. You said the transactions are on different versions of the data, then why do some things affect it immediately?
That's isolation as well, I think, is the answer to your question. I'll try and get back to that, I think. But when you're doing a read, you're allowed to see different versions. Mm-hmm. When you're doing an update, you have to require a lock to update the most recent version. You can't have two people try and update at once. I guess you could technically. That would be something like what they'd call optimistic concurrency control. But then you'd have more unsafe conditions down the road when you try and finally commit.
Thank you.
What about foreign key constraints? Let's say you have a table referencing continent, and you are changing something in different sessions. Well, what's the implications of foreign key constraints on locking?
Right, that's a great question. So foreign key constraints do have to set locking. They have to set shared locks. So what would happen is that if I were modifying a child and I hadn't committed that, nobody could modify the parent to make it out of range while I have my pending transaction open. If that answers your question, it does protect against that case, and it'll never happen.
So is it possible, let's say, that table 2, who references table 1,
yes,
and table 3, who also references table 1, that they're actually interfering with one another, while they're both not touching table 1 at all. Table 2 makes a long, transaction, whatever. Meanwhile, table 3 can't do anything, because of essentially further up the food chain they're colliding. What can you do against that?
I think it is possible. I'd have to put more thought into the specific race condition without lights on me. But yeah, the short version is that some people do run into foreign key locking issues, and they do rely on transactional semantics and correct no bugs in code to enforce those constraints rather than the explicit constraints that you can have defined. I have seen some customers in some situations have to remove foreign key constraints to reduce locking.
So the answer would be not to have foreign key constraints in place at times.
I think I would default to having it, and then I would find a specific situation where it's problematic and maybe remove it. These things that we've shown so far with relational databases, they're great. And databases, a lot of them are actually similar lines of code and complexity to operating systems. And they're more likely to be correct than probably your application code. I think there's like a way of separation of what problems you want to manage versus what you want to let them manage. I would default to say try and have the foreign key constraints. And I could probably tell you offline how to run diagnostics to show you if you're hitting these foreign key errors, and then you could try and turn them off.
Okay, thank you.
Just wondering, when we set up the foreign keys, right, you can set up doing nothing or set up doing like cascadings or updates sort of things. Is that shared locking apply on all of them?
Yes.
Okay.
Yeah. Cool. I'm very happy that I got so many questions, by the way. I think it makes for a more interactive session. So next session, sorry, next discussion point, let's zoom in more on deadlocks and lockweights. So what is a deadlock? A deadlock is a situation where two sessions try to acquire each other's respective locks, and neither can proceed until the other backs down. So the database steps in and says, okay, guys, this is what's going to happen. I'm going to make you back down. And I like to think of the situation of deadlocks as similar to an organization structure, where you have two people that can't work together. And I'll expand on that more in a second, what I mean by that. But the algorithms are the same. So what is a lockweight? A lockweight is one step short of a deadlock. I don't know the analogy here. Maybe it's you try and do something, but it's not in the budget this quarter, and then you ask again, and it's not in the budget next quarter or next quarter. With the default being 50 seconds, and as soon as it's able to acquire that lock, it will. And most transactions that most people have are like, a couple of seconds tops. It seems unlikely that if you try it again in the default configuration, you'd be able to acquire that lock. Deadlock detection works in InnoDB via something called graph detection. We had that little discussion about what happens, where does it kill? Kills the transaction that modified the least rows. And none of those changes apply anymore. They're all rolled back. Preventing deadlocks. I said it was the same as when you have two colleagues argue. They just get in each other's face. What are some potential solutions you might have if two people are always arguing when they're working on projects together? Deathmatch. Deathmatch? I wish I had that in my slide. No, I mean, obvious, right? Don't make them work together. I mean, this might or might not be practical. For your organization to grow and scale, it might not be. But one way might be to reduce the concurrency by having these two things run in isolation, lockstep rather than at the same time. This works, This helps you avoid deadlocks. I should point out deadlocks are actually pretty expensive to roll back, up to 30 times what the corresponding apply would have in the case of the InnoDB storage engine. So a small amount's okay, a large amount could be unhealthy. Solution 2 for these two colleagues arguing, don't make them work on big projects together. So maybe lower the stakes rather than have this multi-year long project and then you discover close to the deadline that nobody's really achieved anything and that the implementation is not acceptable. So in the case of when we were doing these two different sessions and we're requiring locks, locks are held for the duration of the transaction. If I have smaller transactions with smaller pieces of work together, I have less locking. I have less chance of these concurrency conditions arising. I could also apply better indexing. More indexing, less rows locked, potentially. Less of these situations arise. But even though I've provided these two kind of solutions, and they're half solutions, what you should remember is that a small amount of deadlocks are a fact of life. So let's say that we were thinking in terms of the company again. We could have nobody work together ever. How scalable is this? How are you going to grow? You have to implement some procedures like HR or something like that to be able to handle these situations if you want to operate at a reasonable scale. There's this overhead or these disputes that happen, and you just make it part of your operating expertise. So we use the example of MyISM again that I showed at the very start of my talk, where to do that backup, we locked everyone out first. How does this work for concurrency? It's not the most exciting thing, is it? Writes have to be put on hold as soon as I do my backup. I mean, of course, we could say in some MySQL-specific situations, we could back up from a slave and what have you, but deadlocks have to be able to occur at least a little bit for you to be able to have high throughput. So this touches a little bit on optimistic versus like pessimistic concurrency control. The optimist tries everything, and they know of some of the unsafe situations, but then they handle them when they occur. The pessimist tries nothing and doesn't get the same concurrency as a result, but doesn't have to handle these situations. MyISM being table level locking doesn't actually have deadlocks because they just have table locks. The granularity is high enough that it's a single user system. So expect that when the database gives you a deadlock error, I gave you those two strategies, but it's actually your problem. You can't say database is broken, database has to fix that, you have to kind of fix that. And you could ask, why doesn't the database try and reapply the transaction and just rerun those statements? Well, the state has actually kind of changed because someone else was modifying something. So it can't safely do that. It needs to let you step in and you handle these errors as an application developer. And yet, my poll of when I saw a former colleague give a similar talk to this said, how many people handle all of the errors that their application, or that the database gives back? 5% of people raise their hands. So I don't know how, what percentage of people handle all their database errors? I think we're more than 5%. I think we're maybe 10 or 20. It's unfortunate, but this is a common problem. How do you handle lockweight timeout? I would say that you could technically handle it the same as the way a deadlock works. And I did say this point already, that if most transactions are about a second, 50 seconds, it just doesn't seem likely that you'd be able to try that again and it'd work correctly. And when I said actually that it requires it can't replay the transaction safely, and you have to step in and you have to try and do that yourself because state could change, you don't necessarily even have to do this. I think when you look at a typical web application, you'd be talking about a small fraction of a percent that actually gets these errors back, provided you're handling those colleague situations where they clearly can't work with each other. In most cases, I think you would be safe if your database error handling code just gave the user an error and said, nothing's been applied, please try again. I totally think that this is a reasonable way of handling these errors. I do note that there might be exceptions where this might not be technically possible. Say, if you've given a commitment to a user and then you've passed it to a background thread and you have no way of communicating back to that user, maybe my expectation here is unrealistic, like with an asynchronous worker. Some message queues will allow you to like have a two-phase commit where you pop it and then you confirm it. And then you could fail out and then someone else would essentially try it and that would work. If your message queue didn't have that, you would have to find a way to build in code logic to be able to reapply stuff successfully. So that's our discussion of deadlocks. Let's talk about ACID. Let's talk about some of the questions I had about isolation. So all relational databases, they try to subscribe to this acronym called ACID, of intended behaviors. ACID, Atomicity, Consistency, Isolation, and Durability. And some of these are a little bit tunable. I'll go into detail what each one means, but atomic means all or none. I do multiple things at once, I want them to apply like they're one. Consistency, it's kind of generic in what it means, applies to constraints. Isolation, configurable, durable, configurable a little bit. Let's go into details. So atomicity, most people know this one, so I don't have to hop on it too much. It means that if you were to write a query and say, or a couple of queries, transfer money from account A to account B, we can't have like, if it was starting balance of $100 each, we can't end up with one account having $120 and one having $100. Or something that doesn't add up to 200 in total in aggregate. So if you want that atomicity and use a relational database, you just say start transaction, you do your statements, you say commit, we guarantee this. You will not end up in one of those situations where the total between the two doesn't add up to 200. We guarantee it. And there's a lot of stuff in the back end that has to happen for this to be true. Consistency, not too much more to add about consistency other than foreign key constraints, unique constraints, and primary keys. We will never ever allow a situation where we'll be violated where there could be two of one of a primary key, even with this multiversion concurrency control funky stuff happening in the background. In other databases, they stretch this a little bit further, where they might have some check constraints on the domain of data and make sure that it's accurate. This is the promise of consistency. And we gave an example where we might want to relax it because it can be expensive in some situations. Isolation is actually very expensive, what this means. And it can require a lot of locking, and it can require stale data being kept around. So as an answer to this, there's actually 4 theoretical levels or options for what changes you're allowed to see in another transaction while you're modifying data. So these 4 isolation levels, you start off at the very base with read uncommitted, and each one implies the promises of the previous. Where if you configured MySQL to be read uncommitted, if somebody else is modifying data in another session and they haven't said commit, you'll actually see that data. But in terms of what locking we have to do internally to be able to make things happen, it's very low. So the concurrency is very high. Read committed is a step better and generally the minimum of what people expect of what other changes they'll allow to see that people are making. So read committed says that if I read data in my session and then someone else modified data, and then I read the data again in my session, I would actually see their committed change. This is usually considered acceptable. The next one down, called repeatable read, which is actually the default, says that if I read data, and then someone modified and committed that data, and then I read the data again, I actually won't even see their committed change. So this is quite strong for a default, but it's common amongst relational databases. That I should be able to repeat my read, I should be able to see the same data as I saw the first time. So once my session starts, that's the perspective of the data that I'll see with multi-version concurrency control. Serializable, this isn't too commonly used. This is the strictest of choices. And this doesn't use multi-version concurrency control. What it says is that while I read data, I'll lock the data, and nobody else is allowed to make any changes in any other session of the data that I've seen. So I would say for most people, they'll end up in a repeatable read situation, the default, or a read committed situation. And there was a question before that I said I would try and answer and say, how does this kind of affect locking? A lot of people do switch actually to read committed. And the reason they switch is that if you set your isolation level to read committed and you change your binary logging to row-based replication, when you run an update query and the update has to scan through a lot of data but only modify a few rows, with read committed, only the few rows that you'll modify is the ones that will hold the locks open. With repeatable read, everything that you had to examine has to be locked for the duration of your transactions. There is actually a difference that can happen with concurrency. I hope that answers your question, the gentleman that asked it. Yeah. So isolation is configurable. Durability is configurable as well, where what we can say is that by default, actually, when you write data to like a file system, it buffers it, and a buffer is kind of like a funnel. And then when you say sync or commit, then it'll flush those contents down to make sure that it's physically stored on the disk. The problem with these buffers is that these buffers are in memory. So every time you say commit, actually, by default, InnoDB will make sure that those buffers are flushed and empty. But not all databases necessarily will do that. And actually, MySQL does offer the configuration so that you could put MySQL in this mode. If you're not using a RAID controller or you're not using an SSD, this is when it's most visible. And the writes are going to be way worse in the default mode when MySQL is fully durable, making sure that those changes are safe. So that's it for ACID. My last part is a summary, and it's very short. Any questions on the deadlock behavior? It's hard, isn't it? It's last talk of the day. Everyone's probably... I find this stuff fascinating, but maybe not everyone shares my excitement. No questions? Okay. So application responsibilities. Wrap every logical unit of work in start transaction and commit. If you do that, awesome. Responsibility 2 is expect failure, because failure is required for the database to be able to be concurrent. The two failures that you're going to get are going to be lockweight timeout and deadlock. Lockweight timeout, you could retry, or you could handle it like you do a deadlock. Deadlock means that none of the changes that you had made are going to be successful. And that's it. So I have another couple of slides on internal locks to explain that if people are curious, but I was hoping to see if I could get more questions first, because that's really off on a tangent. Question?
About the ACID properties you were talking about in the point of view of one server. What if we have multiple servers? What about the concurrency and dimensional concurrency if I am replicating data?
So you have, so I gave multiple users as the example, just to make sure I'm correct. And I had both users on the same system connecting to the same database. And you're saying, what if the users are on different servers connecting to the same database? Is that
what I was mentioning? If you have multiple databases, so let's say you have a read-write replica, or you have distributed servers, you make changes in one server, and it might not apply into the another server yet.
Great question. So I'll see if I can paraphrase to make sure I'm right. So my example is using a single MySQL server. You're saying what happens if I have read slaves or if I have some distributed architecture like sharding? Do I get these same features? No. Yeah. You only get these features if you're using a single database, which is, it's not impossible, but it's part of the reason why the relational model is it's hard to scale. What generally happens in those sharded architectures is that you break it up into like groups of the problem so that you'll get this isolation, this durability, and everything on a per important segregated problem. So like natural barriers in the data. I hope that that helps. Sorry, you can't do a multi-server. Any other questions? So, one in the front. I'll just wait for Mike.
Going back to the locking, where would you use the? Is it serializable as a default?
Serializable is the doesn't generally make sense one. Right. So, great question. Let me say never, and say when would you need it? Sometimes if you read data and you wanted to make sure that you got the most recent data, so that you could kind of like add salt to the recipe, I guess is a way to explain it, where you need to add something based on the most recent version to write back. You don't want multi-version concurrency control, so you want like the serializable view of that. So if you said select star from my table where whatever for update, you'll actually get serializable isolation just for that query. And you'll get the most recent version of the data. And you'd prevent against a specific race condition where you're modifying the data to write back. Because once you pull that data out, you know, if there's other changes that happen before you write that data back, you could lose those updates. And serializable protects against that.
Hi, on the isolation levels again, the repeatable read, when it says you won't see other sessions, committed rows once your session starts, is that on a transaction basis rather than on a connection to the server?
It's a transaction basis.
Right,
yeah.
okay.
Yeah, so MySQL has a little bit of a divorce between transactions and sessions, but everything here is transactions.
Okay, and are those arranged in sort of order of cheapness of computation to expensiveness?
Yeah, every one here implies the previous.
Right. Okay.
So read uncommitted is just it's cheap. Yeah, it's free.
Hello. You mentioned that there is raw metadata, which is storing the transactions.
Yeah.
Right? Are there any? The first question is, can we read this metadata, or just that's internal? And my second question is there any other data?
Yeah, so it's not in my slide deck tomorrow, but tomorrow I talk a lot about diagnostics and operational stuff. I mean, there are some risks with multi-version concurrency control, right? If you modify data, and then you kept the transaction open, and you took a vacation, like all the future modifications of other data, it has to keep those previous versions of those rows available in case you might want to read them. Like there's a continual background thread trying to clean up old versions of data, and it's got like a hard mark of where it can't advance that watermark past. So there might be some reasons when you want to see that. Certainly in like show RDB status, you can see the age of the oldest transaction. And in information schema, you can see current transactions open that are blocking locks of other people and stuff like that. I don't think I have in my slides tomorrow, but operationally, sure, it's a concern to manage it. You can't do select and then list the column names and see those invisible rows from the table. I can't think of a way to do that. Nor can I specifically think of a good use case in that situation, but you do want to see the lock weights and stuff and how they stack up.
Are these transactions replicated to the slaves?
No. When a transaction is finished, everything is batched up and written in the binary log, on commit. And then it'll be replicated to the slave and replayed then. So the actual state of the pending stuff, and replication is logical, so the actual internal metadata transaction IDs would be different on the slave. But consistency is guaranteed to slaves, so the out-of-ordering thing is protected. Question there?
Maybe you could also explain the gap locks, and well, essentially the general usage when do they occur, and what other operations can they block?
I wish I had a whiteboard. I can explain it, but it's I can't think of an easy way to like draw my hands to do it. The question is kind of, when you use statement-based replication as well, you have to apply actually serializable replay on the slave. Actually, maybe I can think of a way to demonstrate it. Let's say that in session number 1, I said update users set value equals plus 100, where state equals something or other. And then it found 5 users, but I didn't say commit. And let's say in session 2 in that time, I inserted a new user into the state of whatever, and then I said commit. And then things get written in the binary log on commit, so this one gets written first, but this statement had happened, and then it gets committed after. I would actually replay these in a different order on the slave if I didn't have gap locking. So what has to happen here is when you use statement-based replication, still the default, is it has to set additional locking into the range of where state equals whatever, so that nobody could insert into that range until I've finished and committed this, if that makes sense. That's the kind of best I can try. But if you switch to row-based replication and you use actually read committed isolation, you don't have to do that gap locking. And you will get more concurrency.
Okay, so it's only done when, in some mode, not always when you insert.
That's right.
Okay, thanks.
Yeah. I think the guy at the back is first, and that's 2 here.
Why is repeatable reads the preferred default instead of read committed?
I think it's because it's the default on Oracle and other databases. I think it might be history. As I said, I know a reasonable amount of people change it. Assuming defaults is always a tough discussion. I don't think we'll ever change it.
You are showing example when there was a deadlock. What about if you are running a thing in a transaction and you have a trigger in place before update, for example, when the trigger is executed?
Okay. So triggers, what happens is that when you're using statement-based replication, the triggers are just replayed on the slave. The resulting statements from the triggers are not binary logged and the modifications aren't made. When you use row-based replication, it's different though. All of the modifications are grouped together and they're written to the binary log together, and there's no trigger replay on the slave. There's actually a difference depending on the mode. But from InnoDB's perspective as well, because this is the InnoDB storage engine, I don't think it really knows much about triggers. It just knows about row modifications that have to happen. And if everything's in InnoDB, it'll have to apply those locks as you make modifications resulting from triggers. That's the best answer I can think of now. I don't know if there's any edge cases that I'm omitting with that. There was another question here, I think.
Yeah, when we execute a single statement, do we still need to wrap it in and start transaction commit, or the auto commit feature take cares about it?
Yeah, so if you don't ask for it, you get transactions every time. It's just basically like a sandwich. Start transaction, commit automatically is inserted afterwards. Yeah. That's the case for like an update or an insert or a delete. In 5.7, I think even 5.6, we have an optimization where some selects don't have to explicitly do all that setup to create the transactional context. But for the most part, yes. Okay. So my couple of last slides was to say that there was one last type of locking that I omitted. Mutexes, latches, and semaphores. We're going to call them internal locking. And it's not unique to databases, but when you write a multi-threaded program, it actually has to protect against some unsafe situations happening that are not related to rows. They're just related to some operations. So let me try and give some examples. Our buffer pool or our in-memory cache is full. We need to load a page into memory. To load a page into memory, we have to free something from memory, the least actively used item, and then load our replacement in there. But in between us freeing something, someone else could load in and take that spot. So we have to acquire a small lock to be able to say we're doing a modification around our cache, what's allowed to be in memory. So this might be a mutex, for example. Example 2 might be in an index tree, we have pages by default 16 kilobytes each. One might become too full, and it might have to split into 2 separate pages. Well, concurrent system, 2 pages next to each other might have to split, and they might have some problem about who goes first. So in multi-threaded programs, not just databases, you can actually have thread deadlocks as well. So you might have to create some internal locking to be able to serialize that order and make sure that the right person goes first. This is a problem specifically because when mutexes are hot, or when mutexes have high contention, they reduce concurrency. Same as our row versus table level locks, and same as the other stuff we've talked about. And what can actually happen diagnostically is that you see that your database system is something near idle, but you're not achieving more work because everything's blocked waiting behind a lock, and it won't show up as CPU use. This is interesting for MySQL engineering, not so interesting for you, because you won't be able to fix those locks. But peripherally, some DBAs like to have knowledge about this, because they can learn about specific locks that are hot and then find out that they're fixed in subsequent versions, such as these ones here that have been fixed in your MySQL releases. These mutexes or hot locks, this is a big issue as we move into multi-core systems, which has happened for many years. MySQL 5.6 and MySQL 5.5 fix a lot of them. If you're an early user of MySQL and you've got a nice flashy new machine with 16 or 32 cores, you want to upgrade. And the story is better again, obviously, with MySQL 5.7, the version we're working on at the moment. Any questions on mutexes? There's more than that, actually. There's a lot more. I just tried to summarize it. Question there.
I've heard of the mutexes and the semaphores, but not the latches. What are those?
It's just, I think it's an oracleism to describe it, where they have different types of locks and they give different names. But a latch is kind of like a mutex. It's like a, I'm trying to think what the differentiating difference is. I think you would have a latch if you had to protect against something happening from something else that you're doing. I hate that that's recorded, because I'm just going to look stupid.
Thank you.
Yeah, as we've just discovered right now, Morgan is not a storage engine developer. Question?
There are ways to diagnose log errors retrospectively using like the show InnoDB status or whatever. Can you tell us about that a bit more?
Totally. So I showed a deadlock. We saw the deadlock, but it was interactive. Let's say that you came to the system later and you want to know, do I have deadlocks? So I think it was in 5.6 or something, we have a deadlock counter. You can look at that. We also have the ability, I don't know if it's on by default, to write deadlocked statements to the error log. You can also capture that from your application because InnoDB will, or MySQL will hand you back that error message. Then your question is that when you have these two statements and you know that they conflict, or a statement that conflicts, how can you identify exactly which is locking which? The best way, I think, in runtime, it would be, there's an information schema table called InnoDB locks, where it would show which locks are being held by what.
So I have a lock error happening, and I can then catch that, and I can run against a query against information schema on the fly and log this out.
Yeah,
this is what you're saying.
I would probably, technically to do the information schema thing, you'd have to retry them and then see that they're locking and see which rows or which locks are being held by which transaction. But generally, I think I would have to, if you're in repeatable read, if you run explain and you see how many rows it says that it's looking at, it has to lock all of the rows that it looks at. If you're running in read committed, it only has to lock the rows that are modified. I think that's the best explanation I can give. Sorry.
Just a short one. As transaction isolation levels can be set per session as well as globally, if you set them in one session differently as in another, how do locks work?
Good question. So I'm going to skip past locks and say what the real issue of running the more strict isolation levels is you can't clean up the older versions of the rows. I think that's the bigger of the issue. And it'll be dictated by the oldest transaction that's going to basically be the low watermark that's going to block that from advancing.
Okay.
The locks, they're only going to be held when you do a modification because the reads are using MVCC. So if you modify data in read committed, it's going to hold less locks than if you modified the data in repeatable read.
Okay, that's clear. Thanks.
Yeah. Okay. Thank you, everyone.